Welcome to the RhinoCAM Quick Start tutorial series, brought to you by MecSoft. Today we'll be introducing 3-axis milling. Before viewing this video, it is recommended that you first take a moment to complete the Mill Quick Start tutorial. You can find it, among other resources, located on the Learning dialog. From the Rhino main menu, drop down the RhinoCAM menu and pick Learning to display the dialog. The Mill Quick Start tutorial is available in PDF document format. A video version of this document is also available from the MecSoft.com website. If you would like the source files used in this video, just drop us an email at support@MecSoft.com and ask for the intro video source files. We'll be happy to send you a download link. Before starting any new CAM project, you should first perform the following checklist. First, make sure that your part is in the correct units. You can find the units displayed here on the status bar. If you need to change the units, do so before you start programming your part. You can do so from the Options dialog. From the Rhino main menu, select Tools and then Options, and then select Units from the Document Properties section of the dialog. Second, take a look at your part and see if it's in the correct orientation for machining. You may need to rotate your part, for example, to accommodate the table of your CNC mill. Third, check the size of your part. In RhinoCAM, you can do this by double-clicking on the stock icon located under the machining job, and then selecting the Copy Model Bounding Box button. This will show the length, width, and height dimensions of all visible geometry. Fourth, check the geometry type of your part. For 3-axis milling, you should have either solids, surface, or mesh geometry. We will perform the following basic steps in machining this model. First, we will define the machine and the post-processor to use. Then, we'll define the machine setup, including the stock geometry, material, and work 0. Then, we'll select a tool from a predefined tool library to use for machining. After that, we will generate a 3-axis horizontal roughing toolpath. Then, we'll move on to our parallel finishing toolpath. Then, a 3-axis radial toolpath with containment. We will simulate the toolpaths, post-process the toolpaths, and then generate shop documentation. Now, before we begin, I want to mention the layout of the Program tab. You will notice that we will progress from left to right. We'll start with setting the machine, then the post, setup, stock, alignment, material, and then the work 0. Only after those steps are completed do we create machining operation. Let's start by defining the machine to use for this job. From the Program tab, select Machine to display the dialog. Under Machine Type, set the number of axes to 3-axis. Pick OK and notice that the machine type now appears under the machining job in the machining browser. Next, we'll define the post processor. From the Program tab, select Post to display the dialog. For the current post processor, select Haas from the list of available posts. Then set the posted file extension to NC. Other file extensions are available depending on your machine requirements. Pick OK and notice that the post type now appears under the machining job in the machining browser. Now, let's define the machining setup. If there is no setup one listed under your machining job, the system automatically creates one when a work 0 or an operation is generated. However, by default, the MCS, or Machine Coordinate System, is already aligned with the WCS, World Coordinate System, so this step is not required for this part. However, in production, you can have multiple setups and assign different machining orientations for each. In this step, we'll define the raw stock from which to cut the part. From the Program tab, select Stock, and then select Box Stock from the menu to display the dialog. First, we'll select Copy Bounding Box. The system analyzes the part and displays the maximum dimensions of the part. Then we'll set the height to 3.75 and leave the length and width set to the computed part boundaries. Note that the stock dimensions you enter here are measured from the corner of the bounding box selected in this dialog. Pick OK and notice that the stock type now appears under the machining job in the machining browser. If the stock does not display on the screen, select the Stock Visibility icon located at the base of the machining browser. With the stock displayed, we can see that the height of the stock leaves extra room to cut the part in the Z-axis. Once the stock model is created, you can move it in alignment with the part, if needed. From the Program tab, select Align, and then Align Stock from the menu to display the dialog. Since the base of the part is nice and flat, we want to align the stock flush to the bottom of the part. So for Z alignment, we select Bottom, and for XY alignment, we select Center, and then pick OK. The stock is now aligned flush to the bottom of the part in the Z-axis and centered in the X and Y axis. Next, we'll set the material for the stock geometry. From the Program tab, select Material to display the dialog. For material, select Aluminum 6061 from the list of available materials and then pick OK. If the material texture does not display on the stock, select the Material Texture Visibility icon located at the base of the machining browser. Now that the stock is aligned to the part geometry, in this step we will establish the work coordinate origin. This location defines the 0 point from which all toolpath points are interpreted by the controller. From the Program tab, select Align, and then Set World CS. Then select Set to Stock Box. Then set 0 Face to Highest Z and 0 Position to Southwest Corner. This sets the machine home to the top of the stock material and the southwest corner of the stock geometry. Pick OK, and the part and stock geometry are now transformed to the World Coordinate Origin, or WCS. Alternatively, you can use Work 0 to set the work coordinate origin. Instead of moving the part and stock to the WCS origin, this moves the machine coordinate system origin to the specified location. Now, we will define the tools to use for this job. To save time, we will load a predefined tool library. From the Tools tab in the Machining Objects browser, select Load Tool Library to display the File Open dialog. We'll select the predefined tool library named 3-Axis Introduction Tutorial.vkb that we have located in the default data folder, and then pick Open. If you would like the source files used in this video, just drop us an email at support@mecsoft.com and ask for the intro video source files. We'll be happy to send you a download link. The message says the two tools were added, and we see that a 1/2 inch flat mill and a 1/4 inch ball mill now appear in the Machining Objects browser. If you double-click on one of the tools, you see it displays the Create Edit Tools dialog with its dimensions and speeds and feeds parameters already defined. Here we have the 1/4 inch ball mill, and if we select the flat mill icon, we see the 1.5 inch flat mill as well. We will be using the 1/2 inch flat mill for roughing and the 1/4 inch ball mill for finishing. Now we're ready to create our 3-axis horizontal roughing operation. From the Program tab, select 3-axis and then Horizontal Roughing from the menu of 3-axis operations. This will display the Horizontal Roughing Operations dialog. By default, the Control Geometry tab is displayed first, allowing you to define drive and/or containment regions. In 3-axis, this tab is basically used if you want to contain your toolpath to a specific area of the part. In 3-axis, if you do not select anything from the Control Geometry tab, the entire part is used as one drive region. This is what we want, so we'll move on. Now we switch to the Tool tab of the dialog and select the Flat Mill 1/2 inch tool from the list of available tools. Note that the tool parameters of the currently active tool are always displayed in the status bar at the bottom of the Machining Objects browser. Now switch to the Feeds and Speeds tab. Select the Load From Tool button. RhinoCAM will retrieve the feeds and speeds parameters that were set when the tool was defined and associate them with the current operation. Next, we'll switch to the Clearance Plane tab. Set the clearance plane definition to Automatic and the Cut Transfer method to Clearance Plane. In the automatic mode, RhinoCAM will determine a safe Z height for locating the clearance plane. Setting the Cut Transfer method to Clearance Plane will force all transfer moves to be performed in this determined clearance plane. When this dialog is active, the clearance plane is shown on the graphic screen. Now switch to the Cut Parameters tab to control the cutting. We'll leave the tolerances set to 0.01 or 10 thousandths and leave the stock set to 0.025. This means that we will be leaving 25 thousandths of stock remaining on the part and that the actual toolpath cannot deviate from the stock height more than 10 thousandths after machining. For the step over, which is the distance the tool will move per pass in the X and the Y, we'll make it 40% of the tool diameter. You can also specify the step over by entering an exact linear distance. Now we select the Cut Levels tab and set the Step Down control to 50% of the tool diameter. We mentioned that the step over defined on the Cut Parameters tab is the distance the tool moves in the X and Y. Now, the step down specified here is the distance the tool can move in Z. This means that each Z level cut in the roughing operation will remove 50% of the tool diameter, which in this case will be 1/4 of an inch. You can use the graphic illustration displayed in the dialog as a guide for what these values mean. Now we move to the Cut Levels section and we check the box next to Bottom. We don't want the roughing operation to go below a certain depth. You see that the bottom by default is set to -3.75, which is the actual bottom of our part on the table. So we'll set this to -3.5 so that we limit the toolpath to cut no lower than 1/4 inch above the table. This can be used, for example, if you have clamps that you want to avoid. Now we'll pick Generate to calculate the toolpath and display it on the graphic screen. Note that the display of the toolpath in the graphic screen can be turned on and off by selecting the toolpath visibility icon located at the base of the machining browser. With the 3-axis horizontal roughing toolpath displayed and selected, we can now select the Display Toolpath Levels icon from the base of the machining browser. This allows you to look at each Z level cut in the toolpath. You can see here that the last cut level is set at -3.5, just like we wanted. The new toolpath can now be simulated to display the in-process stock model. Switch to the Simulate tab at the top of the machining browser. Select Preferences and set the simulation model to polygonal and the simulation accuracy to fine, and then pick OK. Check Simulate by Moves and adjust the slider to set the simulation speed and then select Play. If you don't want to wait for the entire toolpath, you can select Pause and then To End to calculate and display the entire toolpath simulation. Then we can select the toolpath visibility icon from the base of the machining browser to turn off the toolpath and see the in-process stock model. And there it is, and you can see that it is leaving 1/4 inch of material like we wanted. Now, with the Z-level roughing operation complete, we can move on to the finishing operation. From the Program tab, select 3-axis and then Parallel Finishing from the menu of 3-axis operations. This will create a finishing toolpath in parallel planes. This will display the Parallel Finishing Operation dialog. Now for the Control Geometry tab, we want to contain the finishing toolpath to the bottom profile of the part. To do this, we pick the Select Flat Area Drive Regions button from the dialog. The dialog will minimize and we'll go and pick the bottom surface of the part. Then, pressing Enter or right-click will display the dialog again. The system automatically creates a boundary around the flat surface that we picked and adds this machining region to the list on the Control Geometry tab. Next, we'll go to the Tool tab and pick the Ball Mill 1/4 inch tool from the list. Now we'll select the Cut Parameters tab, and under Cut Control, we're going to set the angle of cuts to 45 degrees. This will set the angle of the parallel cuts to 45 degrees from the x-axis, and for step over, we'll set it to 15% of the tool diameter. Now we pick Generate. Once the toolpath is calculated, we'll select the Display Toolpath Visibility icon again to see the completed toolpath. You can see that it's cutting in parallel planes at 45 degrees, and you can also see that it is contained to the outside perimeter of the base of the part. The new toolpath can now be simulated. Switch to the Simulate tab and pick Play. You can see that the tip of the tool does not pass beyond the perimeter. You can then pick Pause and then To End to complete the simulation, and then hide the toolpath to see the in-process stock model. As we can see from the stock model, we need some additional finishing here in these two pocket features. From the Program tab, we'll select 3-axis and then Radial Machining from the menu of 3-axis operations. This will create a finishing toolpath of linear cuts that radiate out from the center of the pockets. The Radial Machining Operation dialog is now displayed. Now, for the Control Geometry tab, we want to contain the toolpath to the perimeter of each pocket feature. To do this, we pick the Select Drive Containment Regions button from the dialog. The dialog will minimize and we'll go and pick 3 perimeter edges around each of the 2 pocket features. Then, pressing Enter or right-click will display the dialog again. Now we go to the Tool tab and pick the same Ball Mill 1/4 inch tool from the list. Next we'll select the Cut Parameters tab and set the step over to 15% and then pick Generate. This creates a finishing toolpath for these 2 features. As you can see, the linear cuts radiate out from the center of the pocket, and the tip of the tool stops at the perimeter that we selected. Now, with the toolpaths complete, we're ready to post-process to an output text file containing G-codes that can then be sent to the machine tool to actually machine the part. Select Setup 1 from the machining browser, and right-click and select Post. This will post all operations created under the setup. By default, the part file name and the setup name are appended for the G-code file name. Also by default, the posted G-code file is saved to the folder where the part file is located. Now pick Post and the G-code file is displayed in Notepad where it can be viewed or edited manually. Now close Notepad. At any time, you can create an informational report of your machining operations. Switch to the Program tab in the machining browser. Select Setup 1, Right-click and select Information to display and print the report. This dialog provides an estimate of the machining time required for the operations in the setup. You can perform the same right-click sequence on the machining job to determine the estimated machining time for all setups. Now pick OK to close the information dialog. You can also create a setup sheet by generating a shop document. This is typically used to instruct machine operators on how to set up and machine the part on the CNC machine. Select Setup 1. Right-click and select Shop Documentation. Select Template 2 and then click Save. This creates an HTML-based shop document that can be viewed in a web browser. As you can see, this setup sheet template contains a summary at the top, including your stock dimensions, followed by your tool list and then details about each operation. You can perform the same right-click sequence on the machining job to generate shop documentation for all setups. For further assistance, you can visit the online help supplied with the program or visit www.mecsoft.com for additional tutorials. Thank you.